Hello, Kingsport. Debbie, are you there? Hello, Debbie. Can you all hear us and see us okay? Is there anybody in Kingsport that can answer and just let me know that you can hear me? Hey, Mike, can you hear us okay? Hey, Mike, can you hear me? Hello, Mike. Can you hear me?
Hi, Rob.
Did you adjust volumes on our last class?
Oh, I did. I'm glad you remembered that.
Yeah. Just there.
Can you hear us now?
Hey, yeah, good.
That was on our end,
Thank
guys.
That was us. I'm glad you remembered that.
Well, I'm going back to my
I
little
know.
home.
So the first thing tonight is we'll have test 2. That was on Tuesday the 2nd of April, right? And just to make sure we know, chapters are 6, 8, 9, 12, 13, and 15. Now, before you email me and tell me, well, if you put 16 on there on Tuesday, I decided that those 6 would be clean. All right? Remember, you're going to need some version of an ID, your calculator, and as always, the formulas and tables. The test will be 40 questions, A, B, C, and D. Same as the first. So everybody knows where they're going. If you're in section 990, which is the streaming folks, and you told me Johnson City, you're going to Brown Hall 133. That room changed from test 1. And if you're coming to see us in Kingsport, we'll be in room 232. That's the same room as test 1. Now, what I'm going to do for you is this. I'm in D2L here now, all right? And under the syllabus, there's this thoughts for test 2. You know, I posted my thoughts for test 1, and I go down my thoughts to make the test. Thoughts for test 2 will show up at 7 o'clock tonight, but I actually want to take a little look at this with you, all right, because I did this one just a tad bit different than the thoughts for test 1. So the thoughts for test 2, you know, I went by the chapter 6, 8, 9, 12, 13, and 15. That's what we talked about. That's the ones I just wrote down. But notice, I'm pointing you like to page numbers of definitions. I don't know if I did that the first time. I'm pointing you to a page number of the 3 principles of experimental design. I'm pointing you, for example, in chapter 12, where number 4 says to be able to use a finite probability model to find probabilities. In other words, you're using like a nice table. I've given you some problems to look at as reference to say, okay, what's he talking about? Well, here's the style of problem we're looking at, right? Obviously, it won't be the problems that are listed on here. I can't do that. But it will be similar. Same thing for number 5 in chapter 12. And then look in chapter 13, you know, Venn diagram. I'll give you some examples there. Tree diagram, some examples there. Two-way tables, gave you some there. And even out of chapter 15 that we covered on Tuesday, notice I'm pointing you to 2 definitions. And I'm pointing to number 4, I'm pointing you to 2 definitions. And in number 5, I'm pointing you to 2 types of problems. And that 1529B, I think we did that. I'm thinking that was the one about gestational diabetes. So what I'm thinking is I wanted to give you something to reference back to say, okay, if I need to know how to use the sampling distribution to find the probabilities, what kind of problems should I look at? Well, there they are. Again, it won't be those problems. It'll be that style of problem. Like I said, this will show up at 7. 40 questions on the test, just like test 1. Now, before we get into chapter 16, this thing looks familiar to anybody? Thank you. Hey, did it download? Did you get it downloaded on the Mac?
No, I haven't done it yet.
Yeah.
But it downloaded last semester.
Yeah, so it should be fine, right? Yeah. Okay. I'm a little concerned about when we start downloading that mini tab. Look, you understand in D2L there was the instructions or actual Word document, the project, and there was that mini tab file, right? Obviously, you got to download the project, the Word document. You also got to download that mini tab file, and I've told you, you put it wherever you put everybody else, right? All those ones you downloaded out of Sapling Learning where you've been doing the homework problems for me? Yeah. Did we work on number 1? We worked on that on 2. Yeah, can we talk about number 2? So there's a 2E and there's a 2O. Some of you are going to do 2E and some of you are going to do 2O. Whichever one you don't do, would you please delete it out of the project? Just wipe that page out. 2E says if your E number ends in an even number, right? You put your E number in the header anyway. You're going to do this one. Question A of the spring survey asks, what is the fastest you've ever driven an automobile on the highway or interstate in miles per hour? All right. It says create an appropriate graph to display the distribution of the variable called speed. Let me ask you this. The first thing you got to ask yourself, look, one of the reasons I'm looking at the project with you is I can kind of review with you as we go. See, I've got this other thing. You know, you're worried about test 2 on Tuesday. I'm worried about that too, but then I'm worried about what happens on May 2nd. And you're going to do what's on May 2nd. That's when you're final. So, you know, I get a little chance to review with you here. So if I'm looking at how fast you drove, and we're going to call that variable speed, what kind of variable is it? Is it quantitative or categorical? That's definitely quantitative, so you've got two choices here. It's a histogram or a stem plot, and I'm a histogram guy. So look, I already uploaded our Minitab file into Minitab, and I want to make a histogram. We're going to go there. I just want a simple one, and I want speed, right? So again, I'm showing you how to make this graph. If I click OK, in a second the graph pops up, and you're going to see this graph of that quantitative variable speed. Everybody okay with that, right? That's the thing you're going to copy and paste, yeah? And you copy and paste, and it says, which of the following best describes the shape? Is it skewed left, uniform? Uniform would be nice and flat. Is it skewed right, bimodal, or symmetric? What do you think? You got two calls here. You can't tell me that thing's skewed to the left. That thing there is either roughly symmetric or a little bit skewed to the right. And if I was a betting man, I'm going a little bit skewed to the right. Does it have outliers in the thing? Well, it looks like there's somebody stuck out here in the tail, right? Somebody that's driven really slow and somebody that's driven 180 miles an hour. Yeah? Okay. So then, what I would prefer here is, look, you can highlight that, you can circle it, whatever you do, you can bold it, whatever, just so I know which one you're choosing there. It says, using Minitab, calculate the basic statistics, the 5-number summary, and the mean and standard deviation for speed. How do we do that? I'm going to kind of save that guy. I go to Stat, Basic Statistics, Display Descriptive Statistics. That's your basic statistics. I click OK. I tell it speed. There they are. N is the number of observations we have, 621. N star would be any missing values for the individuals. We don't have any of those. We've got the mean. Ignore the SC of the mean. We haven't gotten there yet. There's your standard deviation. And the last 5 there are your 5-number summary, right? In other words, they want you to copy and paste that. Remember, right here there's a menu. You can copy that, paste it where it needs to go in your Word document. It says, choose statistics that are appropriate for the shape of the distribution to describe the center and spread. What statistic would you choose to use to say about the center? Well, if you're saying it's skewed, you better be telling me the median. If you're telling me it's symmetric, and I'm going to, with that problem there, I'm going to take either answer. If you tell me it's symmetric, you better be telling me the mean. It says, in 1 or 2 sentences, why did you choose this? So if the shape is skewed to the right, we know that the mean is influenced by that, so we would use the median. Anytime we have something that's roughly symmetric, we would use the mean. And actually, I should be saying, the problem doesn't say anything about outliers, but if you've got outliers in your data, you should be using the median, right? Okay? What's the value of the statistic? Oh, hell, I don't know. Surely you can read it off what you copied, right? Whichever one you're going to use, the mean or the median. What statistics will you use to describe the spread, the variability? This. Well, if you tell me it's skewed to the right, you better be telling me about the quartiles and or the interquartile range. If you're telling me that you're going to use the mean for the center, you better be using the standard deviation for the spread. What are the values of those statistics? Are there any outliers in this? Justify this using the one IQR rule, right? The 1.5 times IQR rule. Remember we set those fences? Or an appropriate plot. Anybody remember the plot that actually shows the outliers based off the 1.5 times IQR rule? I'm going to get rid of that. The plot I remember is box plot. Simple one. Any outliers in the data? Hell, there's low outliers and there's high outliers, and there's a whole bunch of them, yes? Everybody okay with that? Now that me and you are looking at this, and looking at the relationship of the median with the first quartile and the third quartile, what would you tell me about the shape? The median is closer to the first than it is the third, and we would expect our histogram to look like it was skewed to the right. Thank you for mouthing. You didn't have to say that. I appreciate that. Right? So that was the, look, I'd already cheated. I'd looked at this ahead of time. All right? That, okay, the median's closer to the first, so, you know, when I looked at that histogram and I'm going, oh yeah, I see a little tail going out there, right? I see a little clump over here that looks like we're skewed to the right a little bit. That's the reason I said that. So I just did the problem for the people that have to do E, right? I don't want the people that have their E number ending in an odd number to feel left out. That would be 2-0. Question 4 of the spring 2019 survey asked, there are many health issues associated with the adverse childhood experiences. ACE. Go to this link and take this. What was your ACE score? Look, this turns out to be like kind of a big deal these days. It turns out your ACE score, the higher your ACE score, I mean, it affects your health, how you think, how you work. And I actually went and looked at it and took it myself, and I understand the questions are difficult. Because we're not talking about nice childhood experiences, we're talking about adverse childhood experiences, and so we were just wanting to know that. And to be honest with you, my department chair went to talk at the university gave about this, and the statistics about this is freaking amazing. What your ACE score will tell you about your health and even further down in life. All right? So what we want to do is your ACE score a quantitative variable? And the answer is, yeah, right? The ACE score ranged from 0 through however many questions there were. So I want to come here and I want to make another histogram. This one here is much cleaner than the last one. And what I mean by that is, you'll have no doubt telling me what the shape is. Because this one here looks like the pictures I was drawing all the time. That one is definitely skewed to the right with maybe a possible outlier or outliers, yes? Definitely skewed to the right. Hell, I don't even have to think twice about it, okay? And so we need to do the same thing. We need to get our basic statistics for the ACE score. Display descriptive statistics, ACE. Now the numbers aren't going to be gigantic, right? Because the scores range from 0 up to like 9 or something, yes? So there's my mean and standard deviation of my 5-number summary. Okay, what statistic do you want to use to describe the center? I'm sorry, I'm going to do this for you guys. It's skewed to the right. I'm going to use the median because that's when the median works the best. Why? Well, because it's skewed to the right, we know the mean's pulled further out the tail, the mean's influenced by the skewness, and the median is a more accurate measure of the center. What's the value? Hell, I don't know. It was on the other page there. You'll know because you'll have it there. What do you want to use to measure the spread? Well, if you're going to use the median to measure the center, you've got two options. Give me the first and third quartile, or hell, just give me the interquartile range, right? Subtract Q3 minus Q1. Are there any outliers in the distribution? Either using the 1.5 times IQR rule or the box plot? Hell, I don't know. Let's make the box plot and see. Simple. ACE. Shit, there's a whole bunch of outliers. This time the outliers are all on the high end, right? Okay? We all right with that? So I did both problems. You got to fill in all the stuff, make your choices, do it. I won't do every problem like this, but I'm trying to get you started on the correct foot here with the project. Because the way I see it, if I'm standing here kind of pointing you in the right direction, reminding you of the graphs, being reviewing with you, when the projects come to me, damn, they should look good. I say that. No, I hope they look good. And again, if you don't want to hear what I have to say about it, like I said, it was about the first 10 minutes of class, just tune my ass out. Sorry, I'm just cleaning up the rest of my crap. I don't need this blank, so that's the reason I was cleaning. Now, chapter 16. Folks, we just changed parts of the book again. We're in the home stretch here. We are at our ending part. Now, when I say ending part, there's still like another 7 chapters to go. But where we're at here in this chapter 16 is something called confidence intervals. And it's called the basics. In other words, it's just the beginning here. It's to get us started. Can I say one other thing to everybody, just wherever you are and you're listening? You know the fact that I come here every class day when we got the project and I start talking about the project and I'm kind of pointing in the right direction? I would appreciate that if we could just keep it between me and you guys. I would appreciate that. Because I don't know if you know what goes on in other 15, 30 classes, that kind of shit doesn't happen. So I'm trying to help you. And I get to review with you. That's my whole thought, right? I get to review with you because remember, it's a capstone, so it's like all the kind of stuff we talked about. So that's the reason I do that. But I would prefer that you keep it between us. And you guys are all nodding your head, yes, you know we're recorded, right? Yeah. All my people's got to do is go back and look at last semester or go look at the thing and say, well, that didn't help. Yeah, it didn't. Okay? Now, here's where we're at. We're at statistical inference. I've used that term on you before. Right? Remember, that's where you take what you've learned from your sample to infer back and draw conclusions about your population, right? And so, what we're thinking is that statistical inference provides methods for drawing conclusions about a population from the sample. Now, there's a couple things I want to do here. There's going to be two methods that me and you're going to have, and one of them is called confidence intervals, which is what the title of this chapter is. And when I say drawing conclusions about a population, I'm talking about a population parameter. And when I say from the sample, I'm talking about your statistic. I can't let those two words go. All right? So, like I say, there's two methods, and me and you are going to concentrate on this the rest of the semester. We're going to do it in more than one chapter, these two statistical inference methods we're going to have here. All right? Now, the deal is this. We cannot I'm going to put it like this, be certain that our conclusions are correct. Yeah, I'm going to work on this in like 4 or 5 chapters, and I'm going to tell you up front, look, we're going to make these conclusions about your population parameter based off of your sample statistic, and I cannot guarantee you, I cannot be certain that the conclusions we reach are actually correct. All right? So, we use probability to say how often our methods give a correct result. Now, I'm going to kind of star this just a little bit here, because my thought is this. So what's going to happen is my methods, right, are going to come with this success rate in terms of a probability. A probability tells us how likely something is to occur. So in this case, probability is going to tell us how often our methods are going to give us a correct result. So you got to think about how probability is defined for me and you, right? It's empirical. In other words, you see what happens when you do this random phenomenon or this method over and over and over again, right, to get this probability. It's the proportion of times you get a correct result divided by the total number of times you use your method, correct? That's how we calculate probability. The problem is we're not going to use our method over and over again. We're going to use it once, right? Everybody look at me for a second because I'm not writing. You don't have to write. Here's my deal. I'm not going to use it 1,000 times to calculate this one thing. I'm going to use it once. My problem is going to be is when I use it once, I don't know if that once is correct or not, but I have a probability or a success rate for my method. Okay? I'm going to keep reminding you of that little thought. Because that's kind of a big, to me, it's kind of a big deal here. Now, our two methods we have, I haven't started on either one of them, but chapter 16, to start us here, is a confidence interval. And I would like to get us in our head, what is a confidence interval used for? It's used to estimate a population parameter. That's what a confidence interval is used for. That's what it does. And then chapter 17, which me and you will talk about next Thursday, is something called test of significance. I'm going to put an S. Test. Now, me and you have talked somewhere about, maybe when we did experiments, something about being statistically significant, right? This right here is going to help us with that thought. And test of significance, what it is used for, it's used to assess the evidence for a claim about a population parameter. Two different things going on here. Okay, that's chapter 7. That's our other inference method. Confidence interval is used to estimate a population parameter. Test of significance is used to assess the evidence for some claim about the population parameter. You know, like mu is 12 or some shit like that, right? Okay, we're not trying to estimate anything there. Now, both of these are based on the sampling distribution, chapter 15, of a statistic. So all that about taking a simple random sample of size n and knowing whether the central limit theorem kicks in and tells me that sampling distribution is normal. It has the mean of the population as its mean. It has sigma over the square root of it as its standard deviation, where sigma is the population standard deviation. It's all based on that guy. Now, here's the other thing. I promise you something. I'm not going to show you anything new in this chapter or the next. And you're going, well, how can that be? No. I'm really going to look really hard at things that we've already done. That's the deal here. In this chapter here, there's nothing I'm going to show you that's calculation we haven't talked about, that we haven't done. It's just how I look at it at this point. And then what the hell goes on in chapter 17 is, chapter 17, these test significance, They have their own vocabulary. You know how, remember a experiment had its own vocabulary? Yeah, test of significance has got some serious vocabulary. The calculations and what we're going to do, shit we've already done. It's how we look at it. Okay? Now, before we go any further, what you're going to see me do, every chapter from here to the end of the semester, I'm going to start and tell you what we're going to do. And then I'm going to come and I'm going to tell you what kind of conditions need to be met to trust what we are doing. Right? So in this case, in chapter 16 and 17, we call them simple conditions. Because they're so simple, in the real world, we can't use them. And every time I do this to you, number one is always the same in every chapter. And what it is that the sample you took was an SRS. It was a simple random sample. That's what our methods from now till the end of the semester, or the confidence intervals and the test students we're going to do, are all based off our sample being a simple random sample. 2, what we're going to require here is that our population, distribution, I'm going to remind you your definition. Population distribution means you're looking at the distribution of values of your variable among every individual in the population. You're looking at every individual. You're looking at one at a time here, right? That was the definition I gave you on Tuesday. What we require is that it's normal, or at least approximately normal, with a mean mu. That's where it's centered. And a standard deviation, sigma, right? You're telling me about the variability, about the spread. Okay? There's still nothing here. All right? 3. We don't know the population mean. We don't know where that population distribution is centered. To be honest with you, hell, that's the thing we want to know about, right? That's what we want to estimate. That's what we want to make claims about. We don't know what its value is. But the weird thing is, we do know. You're supposed to ask me at this point, you're supposed to look at me too. How in the hell can you know the standard deviation of the population distribution, but you don't know the mean? Really? Okay. I'm going to write this in blue. Sigma will be given in the problem. That's what's going to distinguish this chapter from chapters that follow here. Now look, you do understand that this, what I've got written here in blue, this is unrealistic, right? There's no way I'm going to know the standard deviation of the population distribution and not know the mean of that population distribution. There ain't no way, right? Okay, all right, I'm going to know about the spread of variability, and I'm not going to know where it's centered. We're trying to say that these are simple conditions. This is not what happens in the real world. Me and you need to start somewhere to see how confidence intervals and test of significance work without having to worry about not knowing too many things. You do understand, if I was really going to try to do this, I'm not going to know that, and I'm not going to know that. We will come back and fix this little assumption we're making that sigma will be known, or it will be given in the problem. But let's work through the language and how all this shit works to start with, and then I'll fix that later, and it's not a big deal, right? See, here's my thing. I would rather have one unknown parameter and one statistic to talk about it, instead of having 2 unknown parameters and then having to know 2 statistics, right? We can fix, that's an easy fix later, once we understand how things work and the language and how the calculation goes. So we'll fix this, what I've got underlined there and what's in blue, because it definitely needs a fix. Now, thinking about this. I'm thinking about the reasoning, the logic of statistical estimation. Remember, I'm getting ready to work with your confidence interval here, right? We're wanting to estimate a population parameter. Now, can we come to an agreement here that for a few chapters, my parameter that I'm going to want to know about in the population is going to be a population mean mu? And the statistic we're going to calculate from our sample statistic is going to be a x bar. All right? So let me get that for you. Mu is going to be our parameter. When we change this, I will point that out to you, but we're not going to change it for quite a few classes. And the x bar is going to be my statistic. I've already got you to write it in your notes like 7 times now that I want to use x bar to estimate mu anyway. Right? I want to use my statistic to estimate my parameter. That's what we're going to do here. We're going to see how we can attack this. Now, I want to read something to you here on the bottom of page 376, and then we'll look at this little example 6.1. The body mass index, BMI, is used to screen for possible weight problems. It is calculated as weight divided by the square of the height, measuring weight in kilograms and height in meters. Okay, who cares? I just know I get this BMI number, right? It says many online BMI calculators will allow you to weigh in pounds and height in inches. Adults with a BMI less than 18.5 kilograms per meter squared are considered underweight. You see how clear that was? No iffiness. If your BMI, body mass index, is less than 18.5 kilograms per meter squared, you are considered underweight. Very straightforward, very clear. The reason I'm pointing that out is because what follows, and those with a BMI greater than 25 kilograms per meter squared may be overweight. It always makes me laugh when 18.5 less than that, well, definitely you're underweight. But if you're over 25, you might be overweight. We won't say you are, but you might. Okay? For data about the BMI, we turn to the National Health and Nutrition Examination Survey, NHANES, a continuing government survey that monitors the health of the American population. Where we at now? This takes me to example 16.1. I need something to work with here. I just don't want to start out crazy with no problems. And it says this. An NHANES report gives data for 654 women aged 20 to 29. Yeah, I quit talking because they just took a sample, right? I don't know if it's a simple random sample yet, but they just have a sample here of 654 women aged 20 to 29, women, 20 to 29. Why do I care about that? Because if my sample is from that group, from that population, I cannot go outside of that population and draw conclusions about men. I can't draw conclusions about women aged 40 to 55. The only conclusions I can draw is about women aged 20 to 29. Do you understand, right? They're telling me about my sample. They sample from that population. I can't go outside of that population and start saying shit about men, women of different ages, children. I can't say anything about other than women aged 20 to 29. Okay? It says this. On the basis of this sample, wait a minute, they calculated their mean BMI. They calculated X bar to be 26.8 from that sample. In other words, they had the BMI of all 654 of these women, and they calculated the average. And this right here, folks, is your statistic. And what they want to do is, on the basis of this sample of 654, we want to estimate the mean BMI mu in the population of all 2.6 million women in this age group. In other words, here, mu would be the mean BMI of all women. I don't care about the 20 point 6 million. All women age 20 to 29. Okay? Right? So that's your population. In other words, what I just write down for you, the notation is trying to tell you this is your parameter. Mu. Yep. Unknown. Now, it says, what do we want to do here? We want to estimate. Well, I want to use X bar being 26.8 to estimate mu. You want me to say it again? I want to use my statistic to estimate my parameter. I want to use what I calculated from my sample to estimate what I want to know about my population. All right? Now, it says, to match the simple conditions, we're going to make some assumptions here to get started. It says we'll treat the in-hand survey as an SRS. Oh, perfect. So what you're going to see me do on these kind of things is you're going to say and go, oh, is it an SRS? They just said, yeah, let's assume it is. Whether it is or not, they're telling me to assume it is. 2, it says from a normal population, in other words, they're trying to tell me that your population distribution is normal. And we'll have to assume 3, that sigma is equal to I'm more concerned with you guys about this part right here. You understand, I read that right out of the problem, right? They told me that sigma was 7.5. I'm not pulling that shit out. That was given to me in the problem like I promised. It says assume it was an SRS. It says assume that the population distribution is normal, and obviously it has a mean mu and a standard deviation sigma. This guy right here, unknown. Sigma was given to me in the problem. We okay, right? Part of the problem is going to be is pulling the information out of the problem. That's always part of the issue. All right? Now, it says this. Okay? I'm going to give you a couple numbers here, and I'm going to lay out how we're going to do this estimating. Number 1. To estimate mu, your population parameter that's unknown, we use X bar. Now, that's just another way for me to write the same thing as always. I want to use my statistic to estimate my parameter. Now, here's the thing. If I just say, okay, I've got a SRS, there's 654, right? The population distribution is normal. The law of large numbers tells me what? That X bar is somewhere close to mu, right? In other words, mu is somewhere close to 26.8. Do we expect mu to be equal to 26.8? Everybody please shake your head. There's no way in hell that your X bar is going to equal that population mean that you're trying to estimate, right? I don't expect it to be equal. I expect by the law of large numbers, with my sample being 654, for mu to be somewhere around 26.8, right? I expect to be halfway close because that's what the law of large numbers guarantees. Now, we can improve over the fact of just saying it's somewhere close, right? Me just saying that, mu is close to 26.8, if I was using statistics language on you, I'd be telling you that's a point estimate. I'm just saying, okay, it's close. We're going to do better than that. And the way we're going to do better is 2. The sampling distribution of our statistic, in this case, of X bar. We know it's normal. How do I know that? I don't need the central limit theorem. The population distribution is normal. The sampling distribution is normal. And I know from Tuesday That's how I figure its mean and its standard deviation, right? Remember, the mean is exactly the same as the population distribution, but we take the standard deviation of the population distribution and divide by the square root of n. In this case, it is n mu 7.5. That's your sigma that's given to me, all divided by the square root of 654. That is your sample size, right? There were 654 women aged 20 to 29. We pull a calculator out, and I believe I get normal, mu, and this guy there is 0.3. We okay? Now, folks, this is the first time all semester you see me write that notation. Normal, mu, sigma, and I didn't put a number in it. Right? Normally, I always know what the mean is, right? I always know where it's centered. Well, that's your unknown parameter. That's the thing we're trying to estimate. Okay? Are we so far so good? That's what I'm just checking. Are we so far so good? Yes. All right. 3. You know I was going to say yes. I haven't got to the punchline yet. Okay? Now, does anybody remember the 95 part of the 68? 95, 99.7 rule? Yes, I'm all the way back to chapter 3. Remember, 68 was 1 standard deviation on either side, 95 is 2 on either side, 99.7 is 3 on either side, right? Remember, every normal distribution satisfies that rule. Okay. Hear what it says, the 95 part. It says X bar and mu are within 2 standard deviations. What is 2 standard deviations? 2 times 0.3 or 0.6, right? Remember my standard deviation was 0.3. In 95% of all samples, that is going to happen. Can I draw a picture? Sometimes a picture is a little better than all the words. And my picture would look like this. There is your sampling distribution. It's normal. The mean is mu. Standard deviation is 0.3. We are centered right there. What does it mean to go 2 standard deviations on either side? It means if you go mu plus 0.6, that's 2 to the right, yes? And then mu minus 0.6, that's 2 to the left. Because that's 2 times your 0.3. And if I was to look at this area here, how much area is there? In other words, that area is representing 95% of all the samples is going to give you an X bar between those 2 numbers. Now, can I be a little bit mathematical? I don't like to be too mathematical, but what this is telling me is in 95% of all samples that you would ever take of 654 women aged 20 to 29 and measure their average BMI, this would be true. You understand? That's what the picture is trying to tell you. In 95% of all the samples you take of that size from that population, X bar is within 2 standard deviations of the mean. X bar is between mu minus 0.6 and X bar is bigger than or equal to, less than or equal to mu plus 0.6. So now here's my problem. What am I trying to pin down here? Am I trying to pin down X bar? What's the thing I'm trying to estimate? Oh hell, I got X bar pinned down, shit. And 95% of all the samples is between those two values. What's the thing I know and what's the thing I'm trying to estimate? Well, the thing I'm trying to estimate is mu, and the thing I know is X bar. That doesn't help me. Right? But let me ask you this, because I'm not going to show you the math here, because that won't help us. If X bar is within 2 standard deviations of the mean in 95% of all the samples, is it true that mu is within 2 standard deviations of X bar in 95% of all the samples? Can I give it to you in something that makes sense to you? If I told you my house was within 2 miles of the grocery store, does that mean the grocery store is within 2 miles of my house? Yep. Right? So, what number was that I drew? That's number 3. Number 4 is this. In 95% of all samples, the following is true. Think about the grocery store being within 2 miles of my house being within 2 miles of the grocery store. Bless you. Bless you. Yeah, I'm going to let that sink in. So the way I think about it, I'll come right back here. The way I think about it is, this is where, my house was within 2 miles of the grocery store. Here is where the grocery store is within 2 miles of my house, right? If X bar is within 2 standard deviations of mu, then I'm going to give you, obviously, mu has got to be within 2 standard deviations of X bar. You know why I keep circling? That's got it. Who's pinned down now? In other words, who's in the middle? Your unknown population parameter that you're trying to estimate. Do we have a value for X bar? Yeah, we get a value for X bar from our problem. Now, you see this little guy here. I'm going to write that down again because I circled the crap out of that one. Right? That's true in 95% of all samples. Right? Now, remember this. We have an X bar. X bar for us was, remember we had 654 women. They found the mean BMI, the X bar, your sample mean, your sample statistic to be 26.8, right? So what happens when I calculate these two numbers? And what I mean is the two numbers on the outside, because I can actually calculate it. What happens when I try to calculate this? I get 26.8 minus 0.6, which is 26.2, right? In other words, that's the left-hand endpoint. If I take X bar plus 0.6, which is 26.8, plus your 0.6, I'm going to get 27.4. Folks, me and you just calculated our first confidence interval. There it is. Now, I got to give you some notation because I don't know how. I know how you're going to write it for me, but I don't know how you're going to see it on the fine, right? And so here is your what I would consider to be a 95% confidence interval for you. That population mean you're trying to estimate. Now, I can write it as 26.2 to 27.4. That's one way to write it. All right? In other words, I'm looking into the numbers on the number line from 26.2 to 27.4, right? Do you understand why it's called a... Right? Because in 95% of all the samples, X bar is within 2 standard deviations of mu. In 95% of all samples, mu is within 2 standard deviations of X bar. That's where the 95% is coming from. We're going to be correct 95% of the time. What I mean is, if I use this over and over and over again, 95% of those intervals will actually contain mu, right? That's the reason we're saying it's a 95% confidence interval. Okay? Another way for notation here to write this is, mathematical is the interval from 26.2 to 27.4. Yeah, those are parentheses. I prefer that one because I'm a math guy, but that's just me. Notice the order I'm writing both of those in. I'm writing from smallest to largest. I'm reading the number line from left to right. I would appreciate that if you, whichever one you use, you would at least put them in the right order for me, right? So then, it looks like, well, we know we're going from here to here, right? I'm going from here to here on my number line. I'm reading from left to right. Okay? Are we okay so far? I'm going to give you a formula here in a minute. I just had to show you where all this shit came from. How do we attack this? Did I show you anything new? And the answer is no. You already knew about the 95 rule. You just needed me to remind you. You already knew what it meant that in 95% of samples, X bar would fall between here and here. Maybe we needed to have a little talk about, okay, if X bar is here between 95%, then obviously mu is between those two values in 95% of all the samples. But I didn't show you anything that was out of control here. All right? Now, my thought is this. I would like to flip over to page 378 and get to the point here about the language, because the calculation, you don't have to remember the calculation. The formula is going to be sitting there looking at you on your 6 pages of formula sheet you always have. All right? And what I'm thinking is, this idea here of margin of error and something else that's called, we're going to call it the confidence level. Okay? Now, every interval that me and you calculate, every confidence interval always has the same form. It's always going to have the form, all right, an estimate Can I do that to you? Does everybody understand what I'm talking about when I write plus, minus like that? In other words, I'm going to take your estimate and add something to it, and I'm going to take your estimate and I'm going to subtract something from it. It makes it easy for me to write the interval if you let me put that plus or minus in the middle there, right? So it's an estimate plus or minus a margin of error. Now look, the margin of error is nothing more than telling me how accurate I believe my estimate is. Your estimate, no matter what chapter I am in, your estimate is always your statistic. In this chapter, your statistic is X bar. So it's going to be an X bar, in this case, plus or minus some margin of error. The margin of error, look, here's the deal. The X bar is sitting right in your middle of your confidence interval, and the margin of error is setting the width. Can I use that word? The length? Right? Because I'm going to take your X bar, I'm going to add your margin of error, and I'm going to subtract your margin of error. The margin of error is controlling the width of your confidence interval there. The larger the margin of error, the larger your confidence interval. The smaller the margin of error, the smaller your confidence interval. X bar don't get changed, that's just where you're centered. Okay? Now, I want to look, there's this little box here on page 378. I'm going to have two boxes here that I'm very interested in on page 378 and 379. 378 says confidence interval. Me and you already know a confidence interval is used to estimate a population parameter. Okay? Now, we speak of a level C, confidence interval. For a parameter. Remember that unknown quantity in the population. Okay? It always comes with two parts. So every confidence interval, meaning you calculate, there's two pieces to it. And I don't mean the left and right hand endpoints, I mean there's two pieces. There's an interval and something else. So there is a 1, right? An interval. Now I'm going to write it down again, hopefully to get this stuck in your head. I promise you it'll always look like an estimate, plus or minus a margin of error. In other words, okay, so half of it is you calculate this confidence interval, and I still haven't written down the formula. What I'm more interested in at this point is number 2. Right? The second part that this confidence interval comes with. And it says it comes with a confidence level C. That's capital C. And what is it? Which gives the probability, all right, that the interval that you calculate in number 1 captures the true, the actual parameter value in repeated samples. Now, you know, I don't always write out definitions for you, and I always warn you when I do, there's a reason. And the reason is this. There's 2 words here that capture my eye. Probability. Actually, there's 3 words. Probability. We only speak of your confidence level and probability. But anytime we ever speak of probability here is when you're going to do this over and over and over again. Me and you're not going to do it over and over and over again. We're going to do it once. Okay? Now, there's one other little thing here in this number 2. The confidence level C, capital C, is the success rate. For the method. In English, the confidence level tells you how often your method will give you a correct result if you do this over and over and over again. Are we okay so far? So it's always going to look like an estimate plus or minus margin of error. It's going to come with this confidence level, and you can think about the confidence level as being the success rate of the method. You can think about it as being the probability that the interval that you calculated captures the true parameter value in repeated samples. Either way, I usually think about it as a success rate. Because when you report this information, you always want to give everybody the confidence level you worked at. Why? Because you're giving people the success rate of the method you just used. You would like to tell people, okay, if I use this over and over again, this is how often I would be successful. And I still haven't said the punchline here yet. I'm just building you up to that because here's the thing. The problem me and you did about 95%. So our C there was, we were trying to estimate the mean BMI mu in the population of all women aged 20 to 29. Your C was 95%. Now I wrote it as 95%. Some people would have wrote it as, hell, it's a probability. And I go back and forth between decimal and percentages with the probability. I will take either. I just want you to know that that's my success rate. Right? This is the probability you track. You capture the true mu in repeated samples. Okay. Our interval looked like this, wasn't it? Oh, I did them separate. Right? There was my x bar plus or minus 0.6, right? That's how I got that. Yeah? I know I did them separate, but you're going to see me write them together like that because that's how my formula is going to come to us. And then when I get ready to do it, I will do each peak separately to get the endpoints of your interval. Okay? Now, what was the interval I got? I got the interval 26.2 to 27.4. That is a 95% confidence interval. The success rate is 95% of the time you're going to capture. Now, how many times did me and you do this? There's my interval. This is the part where students don't like me for a while. Well, maybe you didn't like me to start with. This is where you dislike me more. Okay? When I do this one time, and the confidence level was 95% or whatever in the hell C is, one of two things is true about that interval. Either mu is in there, or mu is not. That was a hell of a thought for a Thursday at 6:30, wasn't it? Dude, you just calculated an interval, level 95% confidence interval, 26.2 to 27.4, and you're going to stand in front of the class and tell me one of two things is true. Either mu is in there, or it is not. You understand? When I say in there, so it's in here, or it's not. It's out here, right? Hell, obviously one of two things is true. It's either in the interval you calculated or not. That's not the part students don't like. The problem is, I can't tell you which one of those is correct. What I do know is, 95% of the time when I do this, mu is in there. 5% of the time when I do this, it's not. You see the one we're looking at? Is it one of the good 95% or is it one of the bad 5%? I don't know. There's no way to know. Right? But I do know that, my success rate here is 95% of the time. Is that one of the good 95% or is it one of the bad 5%? I don't know. So there's language here. And my language is, I'm looking at page 379. And every time I calculate a confidence interval, I'm going to give you the same language over and over again. And it says, interpreting a confidence level. And usually I think about it as interpreting a confidence interval. But I'll go with what they say. In other words, how do I make a statement about this confidence interval where I tell everybody what they want to hear? Or what they need to know, more likely. It said the confidence level is the success rate of the method. I'm not going to write that down again. We don't know whether 95% confidence interval from a particular sample is the one of the good 95 that captures or one of the unlucky ones that misses it. We already had that thought. So what we say is, we say the following. I've got two options what to say. I always pick the first one. We think 95% 95% confident that the unknown mu and I mean the mean BMI of all women aged 20 to 29 is what I mean by the unknown mu, is between 26.2 and 27.4. Now, I'm going to give you this other statement in a moment. That's the one I always use because there's three things here. Bless you. Is it me? You guys are all sneezing. They're not sneezing in the back. I'm giving you the success rate of your method, right? 95%. I am telling you what you are trying to estimate, the unknown mu. Here's the mean BMI of all women aged 20 to 29. What else am I giving you? The confidence interval that me and you calculated. That statement there is giving you everything everybody wants to hear. Your success rate, what the hell you was trying to estimate, and what was the interval you calculated. Another way to say this, and the thing is that right there, that statement written like that, it's got everything in it for me. It says, another way to say it is, we got these numbers, or I guess they're not really saying it to say it this way. It's just, okay, what does that mean? We got these numbers using a method that gives correct results 95% of the time. I'm writing it right out of that box. I always use the one above. I don't like thinking about, oh yeah, we got these numbers. Hell, I want to give you the numbers, right? In other words, that's just confirming that this is your success rate. Now, the only thing I got left to say here is this. All right? I still haven't given you the formula. Actually, the formula is the easy part. All right? Is this. Let's say for the sake of things that I calculate 100 level C equal to 95% confidence intervals. Can I please do that so we can shorten some of that language here, right? For mu. Right? So in other words, I take 100 different samples of size 654. For each one of them, I calculate X bar, and I do that little move we do, and I calculate 100 different level C being 95% confidence intervals. I got them all stacked up here. Right? Okay? How many of those 100 do you expect to actually capture mu if you're doing them all with 95% confidence? We're expecting 95 out of 100. How many are you expecting to miss? In other words, you won't be in there. 5. Yep. If I had them all written down for you, all 100 of them, and we're standing here knowing that we're expecting somewhere close to 95 to capture, somewhere close to 5 missing, if I pull one out, can you tell me if that's a good one or a bad one? No. If I pull another one out, can you tell me if that's a good one or a bad one? What I mean by good is, mu's in there. Bad means it's not. Can you tell me? And the answer is no. The point is this. The only time we speak of probability is if you're going to do it over and over again. You give me 1, the probability is either 0 or 1. 1, mu is in there. 0 is not, and you can't tell me whether it's 0 or 1. Right? That's the reason for this language right here. Now, what me and you need is we need a formula, and we need it bad. So, confidence intervals or a population mean median? I'm going to add something that the book doesn't put at this point. Signals given to it at this point. Now, I'm not going to get all crazy about, we talked about 95%, we went 2 on either side. We were talking about, 68%, we went 1 on either side. We were talking about 99.7, we went 3 on either side, yes? Well, we always don't work at 68, 95, or 99.7. Suppose I want to work at 90% confidence, or 92, or 97, or 85. Can I change that confidence level? Can I change your success rate? And the answer is, yeah, right? I can have any success rate I want. And so, if you think about it like this, what I've got is this. If I want any confidence level, success rate, capital C. Well, what I'm going to do is, how did I do the 95 part? Does anybody know what I just drew you a picture of? Normal, centered at 0, standard deviation of 1. That's your standard normal distribution. Right? We are centered at 0. What I want to do is, I want to capture here, just like I drew that picture about 95%, I'm going to call this your probability C, right? Whatever your confidence level is. I'm going to give you, obviously, out here is 1 minus C over 2, and out here is 1 minus C over 2. How do I know that? Remember, everything under here is 1. This is nice and symmetric. 1 minus C is what outside. If I divide it, half is going to be out here, and half is going to be out there. Right? I want to give these little guys here a name. We know they're z-scores, right? They're z's. This is a minus z, and that is a plus z. We just don't call them z, we call them stars. Right? That's minus z star, and that's z star. I showed you before, at 95%, we went 2 this way, and we went 2 that way. Z star is called a critical value. It comes from your confidence level. It's telling me how many standard deviations do I need to go to the right, how many do I need to go to the left, so that between there is a C percentage, right? The probability is C between them. Yes, that's what it's telling me. Now, are we going to have to calculate this every time? And the answer is no. There is a table C in your... I got to find it. You write that down. I'm going to find our little table. It's in your 6 because I know that because this is the 6 you have. And I called it table C. I know me and you always deal with table A, right? Yep. But if I come over here to table C, I don't care what it's called. What I'm interested in, does everybody see the very last row, confidence level C? That's our guy. You see where it's 50%, 60%, 70%, 80, 90, so on and so forth, different success rates? Does everybody see the left-hand column where it says Z star? So let me ask you this. What's the Z star if your confidence level is 90%? Can you read it? 1.645? What is your confidence level if your, what is your Z star if your confidence level is 99%? Does everybody see 2.576? What the table is telling you is, if you want to capture 90% in the middle here, you need to go 1.645 standard deviations this way, and 1.645 standard deviations that way. If you want to capture the middle 99%, you got to go 2.576 this way and 2.576 this way. What about if you wanted to do 98%? What do? You go 2.326 this way or 2.326 that way, yes? Okay. Please, while I got this table up, look at the 95%. What does it say? It doesn't say 2, does it? It says 1.96 that way and 1.96 that way. 2 is an approximation. That's exact. You want exactly 95%? 1.96, 1.96. Now look, I've shown you the table. It's got different confidence levels. I'm just reading the bottom of that table, and I'm reading the Z star as my critical value. My point is this. We have some favorite confidence levels that we work with. Success rates. We don't want to go much below 90, right? I mean, do you want to do something where the success rate is 50%? Well, just flip a freaking coin in, right? We don't want to do that, okay? And then the Z stars that come off of that table is, this one is 1.645, 1.96. We never use 2 again for 95%. We always use 1.96. And then for 99% is 2.576. Now, how do I know those? Those are our favorites. Those are the ones we always use. And to be honest with you, the one that's most used, and probably the first problem I pick out to do won't use it. People love it, freaking 95% confidence level. Do you got to memorize these? No. You always got that table C, right? Because it's all in your formula sheet. I just want to make sure you knew where to read it from. Now, before we go home tonight, I got one last thing to do. The interval looks like this. You remember, how did I do that? I took 26.8 plus or minus 0.6, correct? What's the 26.8? That was your statistic, that was your estimate. How did I get 0.6? You remember back 6 or 7 pages? Right? How did I get to 0.3? Well, I did that at the beginning, right? That's how I got that 0.3. Yeah? In other words, I'm working backwards to see, okay, so what did he really plug in here? What did he add and subtract? Well, what is this? That's X bar, plus or minus. I'm going to keep writing that 2 one more line. What was the 7.5? And what was the 654? Where did 2 come from? That was the confidence level, right? 95%. That 2 was your critical value. Now, I don't know on your formula sheets what page that's on. You're writing it down. I'm going to go back here where I've got these pulled up. Ah, there it is. Page 2. See where it says basics of inference? The Z confidence interval over population mean, X bar plus or minus Z star times sigma over the square root of n. I don't memorize the formula. It's sitting there looking at it. Now, all I want to know is this, and then we'll go home. If this is my level C confidence interval for mu, where does all the pieces come from? Does everybody know what that is? That is your sample size. It's got to be somewhere in the problem. Does everybody know where this comes from? That's your population standard deviation. This is given. What I mean is it's going to be given to you in the problem. What about this piece here? Where does that come from? That's your critical value. That comes from table C, where you look up the confidence level and you find that Z star. How many standard deviations on either side of the mean do I need to go to capture C%? Where in the hell does that come from? I'm going to give you two options for this. It's either given to you in the problem, in other words, they did the work for it, right? Or we need to calculate. In other words, they gave me the data, and I actually have to add it all up and divide by the total number to find your X bar. Has anybody ever heard the term plug and chug? The language is going to be important to us, and I always make the statement, but it's all about pulling it out and plugging it in and calculating your confidence interval. Be careful going to the house. We're having our test on Tuesday. Remember, the thoughts for test 2 are showing up, right? Everybody knows where they're going. We will pick up here on next Thursday. If you email me the homework, I'll email it back to you. Rob's got yours. I got a couple of them here. The rest of them, I'll get it back to you tonight for midnight, all right? Be careful going to the house. We will see you on Tuesday.